Hello calculus students and general seekers of truth. Welcome to the second video here on finding antiderivatives of e to the x and rational functions that ultimately end with natural log of x. And now we have a slightly more complicated expression, the antiderivative of 3x over x squared plus 1. If you recall, we want to use integration by substitution. Or at least we've done this before, integration by substitution. And the idea here is that you have an expression down here, x squared plus 1, and then you have an expression up here, 3x, and the expression in the numerator is the derivative of the expression in the denominator with a constant multiple. So they're like kind of derivatives of each, one of them is the derivative of each other with maybe a constant multiple. So we want to express this antiderivative using a simpler representation. So we can say that u, make up a new variable called u, is equal to x squared plus 1. The derivative of that with respect to x is equal to 2x. Then we can start rewriting this integral in terms of our simpler variable. So this will be the antiderivative. Instead of x squared plus 1, we can simply write u. Now in order to get rid of all the x's, you see that we have two x related terms here, 3x and the differential dx. So we want to somehow get 3x dx by itself. Well, I should say one more thing is that I guess we're not too worried about the 3. We can just pull the 3 out to the front. We really want to get rid of x dx. Okay, so solve for x dx in terms of u or du, okay, and or du. So we're almost done here. Multiply the right side by dx and divide both sides by 2, and we get that x dx is equal to 1/2 du. So now we can make this substitution in here. This is just a 1, and then instead of the x dx we have 1/2 du. Then we can pull the constants out to the front, so you have 3/2, the integral of 1 over u du, which is equal to 3/2 the natural log of the absolute value of u plus a constant. And remember to substitute back. So this is 3/2 the natural log of the absolute value of x squared plus 1 plus a constant. So there we go. Yet another, just a slightly more complicated example of how we can use substitution. In this next one, number 4, the antiderivative of x e to the x squared. So you can see here that x squared and x are sort of, x is like the derivative of x squared, maybe with the constant multiple. So we want to use x squared as our u substitution. The derivative of that with respect to x is 2x, and now we can make our substitution. So this is the integral of e to the u, okay? And then what's left for us to replace is x dx. Okay. So we multiply both sides by dx and divide by u, and we get 1/2 du is equal to x dx. So we can replace x dx here with 1/2 du. So the antiderivative is 1/2 e to the u plus a constant. And remember to substitute back. U is x squared. Okay. And it is highly recommended that you should check this work for yourself. Take the derivative of our new expression here, and you'll see that it is in fact equal to the integrand. Now, a yet trickier example. This one actually looks simple, but it causes some complications. So a natural starting point is to say that u is equal to x plus 1 quantity squared, and that means du dx is equal to 2 times x plus 1. So we can do certain things like get rid of the denominator, because that's just u, and now we need to solve for 2x dx. Okay? So you get du over dx is equal to 2x plus 2, and then when we try to multiply both sides by dx, we get 2x plus 2 quantity dx. Okay. There isn't any clean or useful way for us to replace 2x dx. Because of this plus 2 here kind of complicates things. And that's okay. Sometimes this happens. So we try something a little bit different. We say that u instead is equal to x plus 1. And so I'm going to erase this. And then we take the derivative. And that means du is equal to dx. Okay? So this is again a second try. We tried u equal to this, it didn't work, so we'll try something similar to that. So now we can get rid of dx and replace it with du. The denominator is easy to replace again. It's x plus 1 squared, or u squared. Now the numerator is, well, let's see, I can pull out the 2. Okay, I can get the 2 out of there, so that's not too difficult. Now I need to replace this x. Well, if we use this part right here, you see that u minus 1 is equal to x. Okay? So it makes it simpler for us to actually make this substitution. Because when you have an addition or subtraction in the numerator, we can actually separate it into two smaller problems. The 2 times the integral of u over u squared minus 1 over u squared du. And there's some more work that requires us to do here. U over u squared is 1 over u minus 1 over u squared, so we can represent this as u to the negative second du. Okay. So we take the antiderivative, 2 times 1 over u, that's the natural log of the absolute value of u. U to the negative second, the antiderivative of that is u to the negative first plus u to the negative first, since that's a negative number. That whole thing plus a constant. Okay? And then don't forget to make the substitution back. So we have 2 times the natural log of the absolute value of x plus 1 plus 1 over u, because u to the negative 1 is just 1 over u of x plus 1. That whole quantity plus a constant. So these examples, they actually look simple, but they're a little bit more tricky than they seem. Okay. Now, we should take a look at one more example. This time we are evaluating a definite integral. So this is evaluated between